This video describes the creation of a 2D thermal analysis model for reinforced concrete column. This slide shows the end result from this exercise, where we see the temperature distribution in the square reinforced concrete column that has 4 corner rebars and that is heated on 3 sides by fire, the 4th side being in contact with air at ambient temperature. In this problem, the column is a square 300 mm by 300 mm reinforced concrete columns with 4 corner bars of 20 mm diameter. The material properties of both concrete and steel follow the laws of Eurocode 2 part 1.2. The section is exposed to fire on 3 sides. The model will be created using the graphic preprocessor GmSAFIR. We will now move to GmSAFIR for creating the model. In GmSAFIR, we start by creating a new project. We select the folder in which you want to save this project, and then we type the name of the project, in this case, thermal concrete. Save, and by default, select Use Geo Extension and Open Cascade. We now have created a project in GmSAFIR in the selected folder. Next step is to create the geometry of our cross-section, 30 by 30 centimeters square reinforced concrete section. So we go into Geometry, Elementary Entities, Add Point, and we'll define the points of the cross-section. We'll start by the lower left corner, x minus 0.15, y minus 0.15. This is all in meters. Z0 and prescribed mesh size, we can leave it at 1. Select Add, and the first point has been created. Next, we'll create point 2 at 0.15 minus 0.15. Point 3 is the upper right corner, and point 4. Actually, point 4, we are going to create a point at 0.15 in order to have a point on the axis of symmetry, which can be used to create a torsion constraint if you want to run a torsional analysis for a 3D structural analysis. And finally, minus 0.15. 0.15 gives us the top left corner. When done, type Q to stop adding nodes. We can go into Tools, Options, Geometry, and General Visibility to show the point labels. Here we have the 5 points. That is correct. Next, we will create lines. We're going to add line. And to create lines, we need to select the starting point and the end point of the line, going in a direction such that the surface that will be created then is on the left, or the lines turn in a counterclockwise direction around the surface. We start with point 1 to point 2, point 2 to point 3, 3 to 4, 4 to 5, and finally 5 to 1. When done, type Q. If we go into Tools, Options, and Visibility, and we look at the normals and tangents, we see that we are indeed turning in a counterclockwise fashion around this surface that we will create later. We will now create the circles for the rebar. To do so, we go into Geometry, Add Circle. For creating a circle, GmSAFIR requires the coordinates of the center of the circle. In this case, the cover to the edge of the rebar is 25 millimeters, and the rebar is 20 millimeter in diameter. So the center is going to be at minus 0.115 minus 0.115 meters if we consider first the lower left corner rebar. Z0, the radius is 0.01, angle 1 is 0 and angle 2 is 2 pi because we want the full circle in the plane of the XY plane here of the model. Select add, and this creates the first rebar. You see it appeared here on the lower left corner. We'll then modify the coordinates of the center to create the remainder, the other 3 rebars. Top right and finally top left. When done, we type Q to abort, and we have our lines for the concrete section and the rebars. Next, we create surfaces, geometry, elementary entities, add plane surface. We select the line 1 as the surface boundary, and next we have to select the 4th circle as whole boundaries because we don't want to include these rebars as part of the first surface, which should be concrete. I select the 4 circles and press E. This created the first surface. Next, I will select one by one the rebars to create as surface boundaries to create the surfaces for the rebar. So this is one, type E. Second, press E. The surface is created. Third rebar, press E. Fourth rebar, press E. When done, type Q to abort. And we now have 4 surfaces. We can verify here with the labels that this all looks correct. This concludes the creation of the geometry. Next, we will assign properties. Let's start with the SAFIR general properties. Here, the problem type is thermal 2D. I do not need to change precision or theta, which deal with the numerical strategy. The initial temperature is 20 degrees Celsius, that's right. I'm going to change the uptime to 2 hours. I don't need to run a torsion analysis. I can leave this parameter unchanged. It also deals with the numerical strategy. The center of the section, it has been created in such a way that this is at the center of the square reinforced column, so that is right. I don't need to offset it. The name of the input file I'm going to change to thermalconcrete.in. The comeback, I will go to a minimum time step of 0.01 second. Again, I want the simulation to run up to 2 hours, and I can allow SAFIR to accelerate up to 128 seconds for the time steps if iterations and convergence is fast. I want to create a TEM file, and this is a case where the fire is defined by a curve, not by a localized fire or interfacing with FDS, so I use curves. With this, our SAFIR general properties are defined. I will now assign the physical group properties by navigating to geometry and now creating physical groups. First, I will deal with the thermal boundary conditions, the fires. I will add physical groups to the curves because boundary conditions are assigned to curves in a 2D thermal analysis. I will create a first group that is called unexposed. I will assign it to line 3 and line 4, which is the top surface of the section which is not exposed to a fire. Press E, and for these, the property type will be a frontier constraint with a condition F20, which means in contact with air at 20 degrees throughout the calculation. Click Add Update to assign. You can close this window and next do it again to create another physical group, this time for the exposed lines. I will select the 3 other lines, 5, 1, and 2. Press E. I am assigning a frontier constraint. In this case, I could also apply the ASTM E119 standard fire, which is what I want to have in this example. But I'm going to show the use of a user-defined gas temperature time curve to illustrate how to apply your own fire. So in this case, you select user-defined, and you see a new box appeared where we have to type the name of the file for the temperature. I'm going to type fire.txt. Note that the extension has to be included, and select Add Update. I can close this window and verify that I applied the boundary conditions as intended by selecting here View Frontiers. We do have F20 on the top surface and fire.txt on the three other sides. Now we defined this boundary condition as fire.txt. We now have to create this txt file where we describe the fire in terms of gas temperature time curve. We navigate to the folder where we saved our project. You see here I have thermalconcrete.go and .j4s from GmSAFIR, which have been created, and I have to create a text file, fire.txt, the same name as specified in the model. And if I open it, you see I predefined it, but here you have to type the times and temperature in seconds and degree, and you can type any value as long as it is in increasing order of, again, the time in seconds in the first number and the temperature in degree C as the second number. And between two defined values, SAFIR would perform a linear interpolation. So here I already inputted the values to follow the standard fire. Thus, we do have our user-defined fire in the same folder as the model for the thermal analysis, and we can go back to GmSAFIR to finish our model. The next step in GmSAFIR is to define the materials of the surface. To do so, we'll add physical groups for surface. The first one will deal with the concrete surface, so I'm labeling it concrete S. Select the plane 1, which is the first surface, the ones for concrete. Type E. I want to assign a material, but the material is not created yet, so I start by selecting new material definition of the type concrete. Here I'm going to select Conc EN 2020, which is the concrete material in the upcoming version of Eurocode. I can change the thermal properties if I wish. Here, let's leave them as they are, but I change the material name, and this is going to be concrete M. Click Add Update twice. You see now a new window that appeared, and we can select now the surface material, concrete M, and click Add Update to add it to surface 1. This material has now been allocated to the physical group that contains surface 1. I can check that here by showing the materials. I will now define a group for the rebars. Let's label it steel rebar surface. We select the 4 surfaces of the corner rebars. Press E. We define a new material of the type metal, steel EC2EN for the steel from Eurocode 2 part 1.2. We don't need to change the thermal properties here, and we are going to call it this material steel rebar M. Add update. With this, we see that we now have two materials name choices. And so for this physical group, we select the surface material steel rebar M. We need to be careful, of course, to use the correct spelling and use exactly the material name as it was defined. We click Add Update, and if we show the materials, we see now that the four rebars are assigned with steel rebar M material, which is of the type steel EC2EN, as we see on the legend at the top left. We can also go into Tools, Visibility, and look here at the physical groups, and we see which type of material is applied to which type of group. For example, if we select only the steel rebars, we find this surface. If we add the concrete, the surface of the concrete comes back. And if we have both, we have the two surfaces. The last step consists in creating the mesh. We will go into Tools, Options, and here in Mesh, we can change the element size factor. Let's set it to 0.2. For this kind of model, the mesh is a 2D mesh. So we click on 2D, and you see that very quickly GmSAFIR creates a mesh. This mesh seems relatively coarse, so we are going to use Refine by Splitting. Click once and you get this mesh. If you are working with the demonstration version of SAFIR, you need to limit the number of nodes and elements under the limit that is allowed by this free demonstration version. So maybe this mesh is appropriate. If you have the full version, you do not have any limitation, and the size of the elements and the number of elements is then a trade-off between the accuracy and computation time. Here, I find the mesh still relatively coarse, especially around the perimeter where the thermal gradients are going to be significant. So I'm going to click once more on Refine by Splitting, and now I am satisfied with the mesh. This concludes the creation of the model. We can now create the .in file that will be used by SAFIR. I click on Create.in file, and the dialog box tells me that everything went well and this file was created. In the folder, I see a thermal concrete.in file that was created. And this file indeed includes all the data and the inputs that SAFIR needs to run the analysis. Toward the end, you recognize the materials that we use with the properties, the time up to 2 hours, and our user-defined fire here that is applied as a boundary condition. We can run this file. One method for running is to double-click on the executable of SAFIR located in the same folder, typing the name of the file, press enter. The simulation runs. You see the time steps. It's going to go up to 7,200 seconds. Then the DOS window closes, and I can see that I have three output files that were generated, a .out, a .tem, and a .xml. I'm going to use Diamond to look at the results in the .xml. First, I verify the model. I do have concrete and steel as I expect, the mesh, the frontiers with one is F20 at the top and fire.txt around here. I'm going to specify a temperature variation from 100 to 900 degrees C with a step of 100, and I can plot the temperature and look at the temperature evolution with time. This looks as expected for this section heated on 3 sides. In Diamond, I can also plot the temperature in a rebar, for example, 1679, and at the center of the section 215. Diamond plots temperature evolution with time, and as well as exporting these data to Excel simply by clicking Ctrl+C and Ctrl+V in Excel. This concludes this example of a 2D thermal analysis of a square reinforced concrete cross-section.